Hello everyone, my name is Rojafari and I would like to welcome you to another video of data mining series. In the previous video we talked about what is regression. We did see the difference between linear and nonlinear regression. In this video we are going to learn about how we would go about validating a fitted regression model. By validating a fitted regression model, what we mean is every time we run a linear regression or nonlinear regression, we manage to estimate some betas, and those coefficients are there, and we can plug and play new data and get some values that are predictions. But how do we know if those values are any good? If our model is significant? Is our model really fitting to the data in a good way? And how much should we trust our the results of our predictions? All of those questions are going to be answered in this video. All right, let's look at the slides. Okay, so in this video we're going to lead by an example and see an example. Run it in R Studio actually. So you want to keep R Studio handy for yourself, so you can try as I'm doing during this video. And we're going to look at two concepts: goodness of fit and significance. And we're going to have two types of significance: joint significance and also the individual significance. We are going to learn about this via an example, so everything will make much more sense. All right. So here was the example that we did see already. We were trying to predict the number of student application for every year using regression, using the previous year football performance, and also the last 2 years average of number of applications. And the dependent attribute here, of course, as we want to predict, is the number of applications in that year. So we are going to use the linear regression here. So this is the equation that we are going to be using here. So basically, this relationship we are trying to capture here, we sort of create this regression equation, which is a linear regression equation. We want to estimate these betas, so we can estimate this relationship using this equation. So that's what we are going to do. We want to estimate these betas, right? So what we have here, this data that shows the performance of football of MSU from 2006 to 2021, and also the previous 2 years average of number of applications. So basically this, for example, this value is the average of these two values, so on and so forth. And then we are going to have the number of applications for that year. So what we are going to try to do here, we are going to use a regression model to capture this relationship. And this is a regression model, and we saw in the previous video, when we fit the model, these are going to be our betas. So these are the 3 estimated betas. So if we put these values for its 2022 for football performance and the SMA and 2, then we are going to get an answer here. That's going to be our prediction. So now here we want to first see how can we come up with these estimations using the R and R Studio. So let's go to our environment in R. So let me switch to R. So here, so this is our environment, and we are going to learn how to load data and do that. One of the first things every time we want to use our studio is to set our working directory. So the working directory that you want to see what it is, you use a code get wd, which gives you the working directory. This basically it says, if you tell me to read a file or something, I'm going to look at this directory. But we don't have to stick with this. We can change or set our working directory. So if you go on session on top and then set working directory, you can actually choose your own working directory. So I'm going to choose my So you have to choose your own in your computer. So once I click, you can see a code is created for you that sets your working directory. So if you now says get WD, that's going to be shown for you, right? So this is a new working directory that has been set. So every time you want to load the data, that's the first thing is that you need to do. Now, this is the code that you're going to be using. I'm going to be using. You will have access to this code, so you can download it and sort of see this code as you have it, as I have it here. So here are these lines of. So the first line of code is to read. We use the function read CSV, and we say this is the file we want to read. So once we run this line of code, we've got 16 observation of 4 variables. So we can actually check what it is by copying this in the console. So we copy this in the console, and it actually sort of shows us our data, which is the same data that we've been seeing, right? And then we say, okay, I want to create a linear model, right? So this is my linear model, and I say this is my formula. This is what the formula is. You have to use the variables that you have here, right? So you have to use exactly these names, right? So I'm saying the number of applications is equal. So this is the way you would sort of convey to this function that your model is this. Is performance, previous year football performance, plus SMAN2, which is simple moving average with n number of 2 years. And this is my data, right? So as simple as that, you introduce your data and your equation to our programming. So once you run this, it creates your model, which is the MSU linear model. Now it's not until when you run this, which is your MSU linear model, that it gives you those values. So it says the intercept is negative 89, 890.711. The previous year football performance coefficient is 5,544.962, and the simple moving average from the last 2 years is 0.0907. Right. So this is exactly what we saw in our slides. If you go back to slide, these are exactly those numbers that we saw in our visual here. So next thing we want to learn how to do is to go about the validation, right? So what we do to get all of those results that we want to use for that purpose is calling the summary of our linear model. So once I run this line, then it gives me a bunch of different things. It gives me the residual, it gives me the coefficients, and I've got the p-value and some other some more general things here. So we're going to for the rest of this video, we're going to sort of understand what each of these are and how are we going to use it. So first we're going to focus on the R-squared. R-squared is a value between 0 and 1, and the closer it is to 1, the better your model has been in basically capturing the variation in your target. And it's 0.94, which is a very good R-squared for any prediction model. So let's go back to the slide and see what R-squared is. So we did this in R, and this is basically R-squared. All right, so R-squared is 1 minus SSE divided by SST. So what are these SST and SST? To understand that, we have to understand what are YI, Y bar and Y hat I, right? So let's use our example to understand what each of these are. So all of these Y target, these are our Y1, Y2, all the way to Y16, right? So these are our Y values. And then, of course, here N is 16. What is Y bar? Y bar is the average of all of our Ys, right? So this is the mean of all of those values, or the average of them. So that's your Y bar. And then what is Y hat I? Y hat I is the prediction, so this is y hat I, prediction of the linear equation for all of those values. So how you would get that? So you would use these two for performance of previous year football performance and SMAN2 to get a value for each of these ones, right? So you're going to be able to get 16 values here. Basically, those are your prediction of your these data objects. Not that we do need a prediction here, but we are going to sort of like use them to see how well our model is actually doing. So these are all values. So we do know what is yi, y bar, and y hat I, and based on those things, what is r squared is showing us is 1 minus on the denominator we have the total variation in the data, right? So this is the total variation in the data. And what is the numerator? The numerator is the amount of variation that was not explained, right? So this is the difference between what is actually the data point, and this is the difference between what was the actual data point and what is the prediction. So this is the total variation that the model could not explain. Right? So basically what r squared is showing us is the percentage of variation accounted by the model. Percentage of variation accounted by the model. And this is a really good way to see how good the model is doing. And getting a r squared of around 94% is a really good r squared. So that's what we know now. It's how much of the variation in our target is being accounted by this model. Now we are accounting for 94% of the variation. If you go back to, we are accounting for 94% of the variation. So that begs the question, if that is r squared, what is adjusted r squared? So adjusted r squared is really, same thing as r squared, but it's been adjusted to account for the number of independent attributes. So the thing is, the more number of independent attributes you add, the r squared is going to increase a little bit. I mean, the more you have, the better the r squared is going to be. But that's not a really good sort of like indication of how model is really showing any good values there, right? So because to be able to sort of like adjust for that number, we say, okay, let's sort of like adjust it, like make it a little bit less. So we are not just encouraged to add, irrelevant independent attributes to the data. So it's very the same thing, but what we are trying to do here is to adjust the values so we are not too encouraged to add too many independent attributes to the model. Here we only have two, and the difference between them shouldn't be that much. If you look at it, it's very similar. It's been, of course, because try to sort of lower our sort of like an expectation of like say, okay, if you have two attributes, but the real what you think, because you have two, it's not one, you have to look at it as a little bit lower value. So that's adjusted r squared. The adjusted r squared, of course, for the model, the regression model, that you only have one attribute, is going to be the same as the r squared. So that's that, and then we do see that it's doing pretty well. So the next thing we want to learn is the joint test of significance. So we're going to have two types of test of significance. The first one is going to be the joint test of significance, which is basically how well the model, the whole model, is fitting to the data. How is the model significant for this data or not? So it's basically the whole model, and for that we get an F statistic, right? So this is that F statistic, and what we really want to work with here is that this p-value, right? Like any other p-value. Like I said, p-value is something that all of you may have a sort of like a certain mental relationship with it, how you go about interpreting it. But the best way to do this is this. Every time it's like sort of like typically the p-value is let me actually do this in here. So every time when we have a test of significance, what we have here, we say H null is there is nothing. There is no relationship. All of these, the fact that what we want is not there. So most of the packaged tests that comes there, H null is there is nothing, there is no relationship, and then H1, the alternative is that there is a relationship, right? So what is p-value? P-value is the probability of the data that we have happening, right? I mean, we are sort of like imagining that the data hasn't happened, but we are sort of like calculating the probability of, if we go back to 2016 and nothing has happened, what is the probability that this is going to be our data, right? Given the null hypothesis is true, right? So if that probability is very small, what does that mean? It means that we have evidence that null hypothesis is wrong. And if that's not the case, it's very small. If it's larger than kind of large, then we don't have evidence to that, right? So one thing we want to pay attention here is the fact that this 0.05 significance level, it's kind of an arbitrary number. It's a good arbitrary number. I mean, when something is less than 5% probability, it's unlikely, right? So you could use it, but at the same time, you want, if you can, sort of like see the situation at the same time, also do some visualization. I think that would be better if you just don't rely on just one p-value. But for the most part, we're going to stick with the 0.5, 0.05 significance level as well. But remember, it's just a really good arbitrary significance level. So let's go back to our R environment. So our p-value is very small. So what does that mean is, if the null hypothesis, which is there is no relationship, were true, the probability of this data that we have happening would be so small. So probably this model is significant. I mean, like, this model is onto something. Like, the probability of the null hypothesis is, this data happening, given the null hypothesis is this small. So we're onto something. Basically, we have enough evidence to reject the null hypothesis. Therefore, we accept the alternative. So that's the joint test of significance. Then we have the individual test of significance. The individual test of significance is actually what we used for when we were using linear regression as dimension reduction, supervised dimension reduction. These are what we were using actually. So let's go back and look at them one more time. So if we go scroll up here, each of the the coefficient comes with a p-value, right? So we look at the coefficient of the p football performance, and then also the coefficient of the p-value of the previous year football performance, and also the coefficient of the simple moving average with N2 of the number of applications from 2 years ago. These are both very small, meaning that they have significance for this model. That means it means that these two independent attributes are contributing in a significant way in the prediction of the number of applications. And then we have a p-value also for the intercept, which basically the same thing is like how important this estimate is. I mean, if we want to use this model, which we should use it because it's like giving us 90%, 94% R squared, and it's significant, we still have to use this negative 890 to use this equation for prediction, for future prediction. But this means that it doesn't mean that if we put these values at 0, we are going to have negative 890 per application. What does that even mean? So that's what that means as far as looking at the p-value of the intercept. But most of the time, what we do look at are these 4 things. We look at the R score or adjusted R score, then we look at the joint significance test, which was the F value and the p value of that, and then we look at the individual significance test for our independent attributes. So we see that everything about this model is really good. I mean, the significance of the independent attributes, the whole model, and the goodness of it were really nice model. So let me offer some summary of this video. In this video, with an example, we talked about what is goodness of fit. We looked at what is R squared and adjusted R squared. And then we also looked at test of significance, the joint test of significance and the individual test of significance. Until the next video.